In this video, we'll get into some of the nitty-gritty details of the k-nearest neighbors, or KNN algorithm. Specifically, we'll explore exactly how we define and identify neighbors. Let's reconsider our KNN model of college graduation rates versus per-student expenditure. In this case, the closest neighbors to any one school are simply the schools that have the most similar expenditures, hence x-axis values. As such, our neighbors are defined by intervals. And these intervals, hence neighborhoods, shift depending upon expenditure. The resulting model is a step function where the steps, hence changes in predicted graduation rate, correspond to changes in the neighborhood intervals. But what happens when we have more than one predictor in our KNN model? For example, suppose we instead model graduation rates y by both expenditures and the typical enrollment in the first-year class. In this case, to predict graduation rate for any school, we can use KNN neighborhoods of schools that are similar with respect to both enrollment and expenditure. Thus, our neighborhoods are now defined by rectangular regions, not intervals. And these regions, or neighborhoods, vary as we vary enrollment and expenditure. In turn, just as when we have one predictor, the resulting KNN model with two predictors is a step function. These steps correspond to where the rectangular neighborhood changes, hence the rectangular shapes here. This image from ISLR captures the general idea. The plot at left represents a KNN model with k equals 1 nearest neighbor. In this case, the model is overfit, passing through each observed data point, represented by the yellow dots. The KNN model at right uses a larger neighborhood of size k equals 9. The resulting model is still a step function, but the surface is a little less wiggly. It's nice to know that the KNN algorithm can handle multiple predictors, but we have yet to answer how neighborhoods are defined in these settings. To this end, we have to consider the feature space in our example, that is, the outcomes of the enrollment and expenditure predictors. For example, consider three schools highlighted here: Macalester College in red, University of Minnesota in blue, and Luther College in black. Focusing on just these three schools, let's check in with our intuition. With respect to enrollment and expenditures, which school appears to be the closer neighbor to Mac, Luther or UMN? You likely answered Luther. Visually, we observe that Luther and Mac have similar enrollments and, in the broader scheme of things, similar expenditures. In contrast, University of Minnesota's large enrollments makes it much less similar to Mac. But we have a problem. It turns out that the math doesn't agree with our intuition. Using the raw data here on enrollment and expenditures for these three schools, let's calculate the Euclidean distance between Mac and Luther, represented by the dashed line. Adding the squared difference in the school's enrollments to the squared difference in their expenditures, then taking the square root, this distance is roughly 5,260 sticks. We can plug this value into a distance matrix. Thus far, we know that schools have zero distance from themselves. So Mac is zero distance from Mac, Luther is zero distance from Luther, and so on. And we know that Mac and Luther have a distance of 5,266. Similarly, we could calculate the distance between Mac and University of Minnesota to be 3,617. And the distance between Luther and the University of Minnesota to be 7,751. Stepping back then, notice that our math indicates that, contrary to our intuition and the visual evidence, University of Minnesota is the closer neighbor to Mac, whereas the distance between Mac and Luther is 5,266, the distance between Mac and UMN is only 3,617. So how did this happen? Well, our distance measurements didn't take into account the two very different units and scales of our two predictors. First, enrollments are measured by number of students, and expenditure is measured in number of dollars. Second, consider the scales. On the scale of enrollments, the difference of 3,072 students between MAC and UMN is relatively large. Yet on the scale of expenditures, the difference of $5,264 between MAC and Luther is relatively small. Yet our metric didn't consider scale or relativity. It simply noted that 3,072 is a smaller number than 5,264, thus determined that MAC is closer to the University of Minnesota. Luckily, the fix is easy. We can standardize our predictors. This puts them on the same scale so that one predictor doesn't exert undue influence on our distance metrics, hence the definitions of our KNN neighborhoods. To standardize the outcomes of some predictor x, we can subtract the mean x value and then divide by the standard deviation of x values. The result then measures the number of standard deviations that an individual outcome falls above or below the mean outcome. As an example, let's standardize MAC's enrollment and expenditure values. To begin, MAC's first-year enrollment tends to be around 452 students. By comparison, across all 775 schools in our sample, enrollments vary around a mean of roughly 781 students with a standard deviation of 930 students. Subtracting this mean from MAC's data point and then dividing by the standard deviation indicates that MAC's first-year enrollment is roughly 0.35 standard deviations below average. Similarly, when comparing MAC's per-student expenditures to those of all 775 schools in our sample, we learn that MAC's expenditures are nearly 1 standard deviation above average. Across all schools, then, we're taking the enrollment and expenditure data from the original scales of people and dollars to standardized measurements on the same scale. The vertical and horizontal lines at 0 represent the average enrollment and expenditure values. For example, on this standardized scale, notice that the University of Minnesota has above average expenditures and above average enrollments. The standardized predictor values for these 3 schools are summarized here. From these, we can calculate the standard Euclidean distances between each pair of schools. Revisiting the question of which school is closer to MAC, the answer now correctly matches the visual evidence and our intuition. Whereas the standardized distance between MAC and UMN is 3.32, the standardized difference between MAC and Luther is only 1.04. In conclusion, this video illustrates that details matter. This particular detail about how to calculate distance will continue to be relevant to other algorithms that we learn throughout the semester.